UC Berkeley. He's going to talk about emergent phenomena in thermal transport. It's phonon thermal transport. He's going to talk about hydrodynamics in new materials. So I'm looking forward to your talk. Thank you. Maybe you ask.
Okay. Thanks for the introduction and thanks for having me here. So today I'm going to talk about some of the results that I've been working on for a good part of my PhD project. And just to give a brief outline, I think I'm going to introduce and talk very quickly, just a reminder of the Boltzmann transport equation, which we have seen already quite some times. I will go again through the reasons, at least from my viewpoint, of why the relaxation time approximation fails, and we'll try to cure this failure. And for doing that, I will introduce this concept of relaxons. I will also try to talk about some very recent work I've been doing about trying to understand a more improved description of surface scattering. And then if time allows, but I don't think, I will briefly touch also second sound. And just since I know that I will not have the time at the end of the talk, I just briefly acknowledge a bunch of people that have helped me in this work. So Nicola Marzari, that has been my PhD advisor. There's been some collaborators in Paris, Francesco Mauri, Michele Lazzari, Lorenzo and Giorgia, with which some of the ideas that I'm going to talk about have been developed with. And also let me thank also Stephen Louis, which is my current advisor and helps and allowed me to still be working on some topics related with transport. And also funding, which is mainly coming from Switzerland right now. Okay, so let's start with the fundamentals of the semi-classical theory of thermal transport. So just to get, again, familiar with the notation that I'm going to use. So n bar is the Bose-Einstein distribution function. Mu is just an index that will label all possible phonon modes, so a label over all possible phonon wave vectors and phonon branch indexes, mu. Again, I want to study thermal transport, so we want to apply a thermal gradient on top of our material so that the phonon population is not anymore going to be described by the Bose-Einstein distribution function, but there's going to be a deviation out of equilibrium, delta n, that we need to compute if we want to characterize thermal conductivity. And one way to do this is, of course, solving the semi-classical Boltzmann transport equation, which is basically a closed expression that you can use and solve in order to obtain this out of equilibrium distribution function for phonons, which is made basically by two. It's a balance equation. So you have on the left the diffusion or Liouvillean operator, which describes how the phonon state will evolve in time and space due to the action of a certain phonon group velocity. And this is balanced on the right side by the collision matrix. Note also, just a technical detail, but note that the scattering matrix acts only on the deviation from equilibrium. And this also one could say that the Bose-Einstein distribution is not a stationary distribution for the linearized scattering matrix. This is more technical for those that are expert about it. And also let me point out, just to make a point with the previous talk, this equation is irreversible in time. So if you reverse the time coordinate, the system does not go back to the point where it started from. And also, you can derive the Boltzmann equation from the Kadanoff-Baym equation. So you have actually a way to derive these formulas systematically for what is currently known as the best way to include thermodynamics in quantum mechanics. It's essentially derived from something which is analogous to the Schrödinger equation for thermodynamics. Okay, anyway, going back to the point, so something more of the topic of the discussion is we have to solve that and get the out of equilibrium distribution function of phonons, and then you can get an expression of thermal conductivity, which we have seen within the harmonic approximation. This is given just by the product of the number of particles times their velocity times their energy that they are carrying. This is easy. The problem is, of course, solving that Boltzmann transport equation. Just again, quickly recalling that I will be using in my results 3 phonon scattering rates. So I will include the presence of decay and coalescence at the 3rd order in perturbation theory in terms of phonons. And also I will include the effect of isotopes. So the presence of isotopes means there are mass defects, so deviation from the perfect crystal, which will induce some scattering. You can derive with the Fermi-Golden rule the transition rates for these events. You can use these to build the scattering matrix and construct the complete expression for the Boltzmann transport equation. And also to construct, to compute these properties, you also need to know the phonon frequencies and the strength of the interaction, which is something which we do from first principles, so you can get the dynamical matrix, which has been introduced also in the previous talk, from density functional perturbation theory, and also this 3rd derivative can be obtained with density function perturbation theory with a recent implementation that has been released in Quantum Espresso not so long ago. And the advantage of doing this from first principles is that we don't have to use any fitting parameter to the Boltzmann transport equation, so we'll just get numbers and then we'll be able to compare directly with the experiments and try to understand actually, and try to get some extra insights in our results. Okay, so now going into more the more interesting part of the work, so let's recall again the relaxation time approximation, which we have seen sometimes appearing today and yesterday. So mathematically, the main reason you want to introduce this expression is because the complete expression of the scattering matrix is too complex. So you want to simplify the expression, and basically you drop the out-of-diagonal matrix elements. So of course, one integral goes away, and you have something which is much simpler to deal with. So simplicity is the reason why you introduce this approximation. And the diagonal matrix elements also have the meaning of the phonon lifetime. So they actually coincide with the interval. This tau represents also the average interval of time between 2 consecutive phonon collisions. Sorry. Okay, you can use this expression, put it into the Boltzmann transport equation. You can solve that analytically, and you are probably, most of you, familiar with this expression of thermal conductivity, which is just given within this approximation as the product of the phonon-specific heat times the group velocity of the phonon times the mean free path. Mean free path, which is the average distance traveled by the phonon between 2 consecutive scattering events. Now, actually, starting from Pyers, I think he was the guy who actually recognized that this is basically an expression which is extremely similar to the expression for thermal conductivity, which Maxwell, I think, derived when he was studying the kinetic theory of gases. And so, actually, I think that starting from this analogy that Pyers introduced this notion of the phonon gas, which we are still discussing to some extent, all of us, still today after more or less 80 years since the work of Pyers. Okay, but of course this comes with some approximation. So we simplified the scattering matrix, and what we see is basically that the result, this thermal conductivity, is roughly speaking proportional to the phonon lifetime. This means that you are making the hypothesis that every time there is a scattering event, the heat flux is dissipated. So the rate of the heat flux dissipation is the same of the phonon collisions. And as also has been discussed somehow yesterday, this is not, strictly speaking, correct, because you have to take into account the distinction between normal and Umklapp processes. So you have normal processes in which the wave vector of phonons are conserved during a collision event, whereas in the Umklapp case, you have the translational periodicity of the system that allows you to have also Umklapp kinds of events, so that the momentum of phonons is not, strictly speaking, conserved. And this is relevant in terms when discussing with thermal transport properties, because you can prove that on average, not only the momentum, but also the heat flux is going to be conserved by normal processes, whereas the Umklapp don't conserve that. Now, in general, for most cases, you might even be happy and try to forget about the differences between these two processes, but sometimes you cannot do that. So if you, for example, try to get the thermal conductivity of graphite in the in-plane direction, using the relaxation time approximation, you get these dotted lines. The experiments are these dots, which are up there, and you can only get to those values if you are able to solve and evaluate the thermal conductivity using the complete expression of the scattering matrix. I still didn't explain how to do that, but some of you are already familiar with several ways you can get these points. Basically, for example, at room temperature, you get off by a factor of 4 if you use the relaxation time approximation and neglect a problem at the level of the theory that we are using. So it's the method which is not suitable. Okay. All right. Okay, so here we go. Okay, so we have this large difference in graphite, and now as you reduce the dimensionality and try to go and study graphene, so single and bilayer, now the problems are just getting worse. So you have, actually at room temperature, the value of the thermal conductivity of graphene is actually off by an order of magnitude, so it's way off than before in terms of numbers, but also you get wrong trends in using the relaxation time approximation. So if you use that, you would expect the graphite has the highest possible thermal conductivity between bilayer and single layer graphene. And instead, if you use the exact solutions of Boltzmann transport equation, then you get even the opposite trends. So you're both quantitatively and qualitatively incorrect. And of course, the reason that you see this behavior can be traced back to the presence of normal processes. So here I'm plotting just an average scattering frequency for different processes. So I'm distinguish normal, Umklapp, and isotopic scattering events. And here you can see that at any possible temperature, the normal processes, the red line, is what happens, what takes place with the highest possible frequency. So it's the most likely event you're going to see, not just at low temperature. So because at low temperature you expect to see some kind of Umklapp freezing, so that it's usual to see a lot of normal processes, but you see this behavior extending to room temperature and even above that. And if you now extend the study to other two-dimensional materials, here I'm just adding a bunch of other graphene, boron nitride, fluorographene, and MOS2, you see the same behavior, same failures to various extent of the relaxation time approximation, which is going to always give you values which are very far off from the exact expression of thermal conductivity. Also, just to give credit, this failure was first found in graphene by Lindsay and others some years ago. And in all these cases, you have the same behaviors. You still have a lot of normal processes that dominate the phonon scattering dynamics. Now, it's interesting actually to look at why is this interesting, because this is quite different from what you could expect to see in general in three-dimensional materials. So if you try to study what kind of transport regimes you expect to see in a conventional three-dimensional solid, so you could think something like silicon, you expect various thermal transport regimes. So you start at very low temperature in conditions where there's no phonon scattering taking place, and not among different phonons. You only have phonons that are free to propagate, and every now and then they will hit the surface, and that's where the heat flux is going to be dissipated. This is the ballistic regime, which takes place at very low temperatures, so cryogenic helium, liquid helium kind of temperatures. And now if you increase that a little bit, you may end up in this Poiseuille regime in which you still have the heat flux which is dissipated at the surface of the sample, but now you also have a lot of normal processes taking place inside the material which are going to conserve momentum. They're not going to be contributing significantly to the heat flux dissipation, only when the phonons will hit the surface. That's going to induce some thermal resistivity. And this is called Poiseuille, or a hydrodynamic regime, because of the analogy with the real fluids. If you think at the flow of water molecules through a pipe, you also have water molecules scattering among each other elastically, so conserving energy and momentum, and only when the water molecule is going to hit the surface, you will have some dissipation of flux taking place at the surface. Now you continue increasing the temperature, you end up in a Zeeman regime, so now the walls of the pipe are not felt anymore. Now you still have a lot of normal processes, but now the heat flux dissipation is contributed to by Umklapp scattering events. And eventually you end up in a kinetic regime where you only basically have Umklapp processes, so as soon as the phonon is having a scattering event, the heat flux is quickly dissipated. And that's also typically where you expect the relaxation time approximation to work. Okay, now if you look at graphene, well, the situation is drastically different. So you have that while in three-dimensional solids, sometimes, in very rare cases, you can observe these Poiseuille and Zeeman regimes at very low temperatures. Well, in graphene and other two-dimensional materials, the situation is drastically different. And these cryogenic conditions are actually observed at room temperature conditions and even above. So you have these hydrodynamic kind of regimes which exist at room temperature conditions approximately. And basically you have the same physics, cryogenic temperatures in 3D being carried over at high temperature in two-dimensional materials. And I think tomorrow we're going to hear about some other consequences of this kind of transport regimes. So now what I'm going to focus mostly is that we have to deal with these conditions in which there are a lot of normal processes. So normal processes that don't dissipate heat flux. So in some sense, you cannot really you look at the phonons and use that as a meaningful relaxation time to understand what is the heat flux dissipation, what is the right time scale at which that phenomenon is taking place. And so more generally, our idea was that not only just to find the best relaxation time for phonons, but was really just to understand what is the right way to think at the heat carrier. And our idea, our proposal was to introduce new objects and start from the diagonalization of the scattering matrix. So if you take this matrix, it's something that, it's a matrix, just numbers. You can diagonalize it and get a set of eigenvectors, theta, and a set of eigenvalues, 1 over tau. Alpha is just an eigenvalue index, which comes out of this diagonalization procedure. And I'm going to show, basically, and discuss some of the properties of these eigenvectors states. Now, since by construction we are introducing these eigenvectors, these objects as eigenvectors of the scattering operator, these eigenvectors do not scatter one against each other because they make this operator diagonal, so almost by construction. And so the next step is to realize that each of these eigenvectors actually corresponds to a collective excitation of the system. To think about that, the easiest way is, well, look at this guy here. What we have is a function theta of alpha and mu. So alpha is an eigenvalue index, so let's just decide to fix one particular eigenvalue. So alpha equal to 1. What we are left with is a distribution function, theta, is a function of every possible phonon state mu. So you have actually something that is a phonon distribution function. So this describes actually more specifically the way that each phonon is going to be displaced out of equilibrium by the action of this eigenvector theta. And just to give a practical example, here I'm showing what happens in graphene at room temperature. So you have this hexagonal object here is the Brillouin zone. And this object here, all of these branches belong to the same eigenvectors because this index mu spans over all possible phonon states. And these colors here indicate how phonons are displaced out of equilibrium. So for example, in this particular case, you have this particular eigenvector which is going to displace a lot of phonons out of equilibrium in the long wavelength region. Red means areas that are going to be overpopulated with respect to equilibrium, and blue indicates depletion. And it's not just long wavelength ZA flexural modes of graphene that are belonging to this relaxon, but you see also contribution coming from transverse, longitudinal acoustic modes, and also, although not shown here, also from the remaining optical branches. So basically, you have an object which couples different phonons, and you can think of it as a collective excitation of phonon. Now, the next step, if you want to be more quantitative about the results we're going to, is basically to make a change of basis. So rather than having a look at the Boltzmann transport equation, as we were doing before in terms of these occupation numbers of phonon states, well, what we do here is going to be introducing an occupation number, f of alpha, which is associated to each of these eigenvectors, theta alpha. And just to avoid saying every time eigenvectors of the scattering matrix, let me just call these objects relaxons. Okay, so now rather than focusing on the occupation number of phonons, we want to focus on the occupation number of relaxon, f of alpha, and you use this expression to rotate the Boltzmann transport equation. So you rotate it, you have an expression of the Boltzmann equation which is equivalent to the previous one. It's just that now we lost any remaining trace of phonon indices. We're just left with an expression in terms of the occupation number, f of alpha, which is associated with each of these relaxons. And we have to do some integrals over this alpha, so this eigenvalue index, while before we were doing integrations over phonon states. Now, if you just look at this equation, you could even argue that it looks even more complicated than it was before. But of course, we can give some extra insights to the physical properties in terms of these objects. Yes? Okay, so I don't have a slide on that because I prefer to skip these details. But anyway, just to explain a little bit in more details this expression here. So you have, of course, you can recognize the scattering operator on the right, which now is a simple object because by construction we diagonalize that. What is on the left is the diffusion operator. And to understand why there are 4 terms, while before I just showed you 2, probably I can be more precise explaining it from this equation here. So here you have 2 terms, right? But then you also have the expansion of the distribution function, which is composed of 2 terms. So the Bose-Einstein plus the deviation. And so you have the derivatives associated to the Bose-Einstein distribution function plus the derivatives associated to the out of equilibrium part, and that's why you have 4 terms. And then there are some other technicalities about, of course, how you do this rotation, but you can find these details also in the article if you, or we can even discuss that later if you want the details. Yes.
So one question I have is about the diagonalization process. So is there any aspect of that matrix that is inherently temperature dependent?
Yes.
Okay, so does that mean your basis changes at every temperature?
As a temperature, yeah, as a function of the
I
temperature.
see.
So each different temperature point requires a different
Basis.
a recalculation of the diagonalization procedure, and therefore a different basis set. Yeah.
So like the picture you showed of which, I guess I think of it as modes, but which phonons contribute to the relaxon, that plot would then be temperature dependent as well, right?
Absolutely, which is also something which you kind of know that you should expect, because at low temperature there's going to be more acoustic phonons contributing to the physics and different stuff at other temperatures.
Do you see any logical progression in the way that plot looks as a function of temperature? Does it follow any particular trajectory in the way that those shapes evolve with temperature?
I should, it's not easy to just give the intuition, but you can expect at high temperature, so when you go close to the classical limit, that I think that there are some Bose-Einstein distribution function appearing inside the expression for the scattering matrix, which if you expand at high temperature, then you see that the temperature dependence is just like something like 1/T. And so at high temperature, you expect that these eigenvalues are going to probably go down as 1/T. And of course, the low temperature is where you have to be careful and consider everything in a detailed way. Excellent question. Yeah. The assumption is that the Boltzmann transport equation holds. That's the only assumption, because then you can prove that diagonalization is always possible due to the fact that that scattering matrix can be shown to be symmetric and positive definite, and that mathematically ensures you that you can always find a set of eigenvalues and eigenvectors, and those eigenvalues are actually going to be real and positive definite, and the eigenvectors, you can prove they also have a well-defined parity, so they are going to be either even or odd upon inversion of the phonon wave vector.
Then one question I have is, in my understanding, relaxon is collective motion of phonon particles, right?
Mm-hmm.
Then can we still use the concept of relaxon for the case where the time period is shorter than normal scattering rate and the spatial length scale is shorter than normal scattering mean free path?
Sorry,
So basically, relaxon, in my understanding, relaxon is collective motion of phonons, right?
Mm-hmm.
So basically, it assumes you are the relaxon can be established by many scattering events, right? So my question is, can we use the concept of relaxon when the time scale is shorter than normal scattering rate, normal scattering relaxation time, and the length scale is shorter than normal scattering mean free path, where the scattering rarely happens?
That's a very tricky question to answer. I would say that this is very closely related with the assumptions that you do when you write the Boltzmann transport equation. So that's very closely related with the condition of validity of the Boltzmann transport equation, which are by no means trivial, and I cannot say I understand very well all the details of when semi-classical transport applies and when it fails. But certainly, yes, if you expect to describe things like mean-free path being much shorter than the interatomic spacing, or a time-dependent evolution which happens at the femtosecond scale, now for sure those are conditions that will fall out of the limits of validity of the Boltzmann transport equation, and therefore everything that I will be saying afterwards just crumbles down and goes out of the limits of validity of the theory. Yeah. Which
Thank you.
you cannot have a generic theory. Yeah. Semi-positive definitely, so it can be greater or at most equal to 0. It basically derives due to the fact that the scattering matrix is made out of transition rates, which are probabilities which are positive or at most 0, and from these you can actually prove that the matrix is in fact semi-positive definite, and hence this condition on the eigenvalues. But it basically derives out of the fact that we are dealing with probabilities which are positive. Okay, so if no other further questions, then I'll just try to make use of this equation to get something more interesting that we couldn't understand previously using the relaxation time approximation or the basis of phonons. So one is the existence of exact relaxation times. So if you take a system now, you imagine that it is spatially homogeneous, so there's no space dependence. So this means that these spatial derivatives can be set to 0. And also you imagine to leave the system at a constant temperature, so also this time disappear, and basically you drop a lot of stuff, and you're just left with a very simple differential equation for a time evolution of the relaxon occupation number, which of course is characterized by an exponential decay time, and the decay time is exactly this eigenvalue of the scattering matrix. And this is precisely the definition of what is relaxation time. So something that it will take a time tau for decaying by a factor 1 over e. Right, so relaxons are characterized exactly by relaxation times. And of course, if you rotate back these results into the basis of phonons, you can also see that the time evolution of the phonon occupation number is going to be determined by a linear combination of several exponential decay rates with coefficients which have all possible signs and will change from one relaxon to another. Basically, this can be any decaying function, not necessarily an exponential rate, and therefore you cannot define rigorously the relaxation time of a phonon. Just let me also be clear that the phonon lifetime still exists and can be well defined. We have to also have in mind the distinction between the lifetime, which is a property of the system at equilibrium, and the relaxation time, which is a thermodynamical information, which comes out of something like the Boltzmann transport equation, for example. Okay, so, and the other interesting feature that you can get is the bulk thermal conductivity. So for this system, instead we suppose that there is, we are at steady state, so this time derivative disappears. And also we are dealing with a bulk system, so there will be translational invariance, and therefore you expect also that the relaxon population will not depend on the position that you are looking at inside the system. And so you drop a lot of things, and that's what you are left with, which is a very simple way of dealing with a bulk solution of the Boltzmann transport equation. This is something that you can get exactly, just multiply, bring tau on the left side. Of course, as an advantage with respect to the relaxation time approximation is this time we're not adding any other approximation on top of the Boltzmann transport equation. And you can use the result and plug it back into the definition of the thermal conductivity. You do a lot of algebra again, but the end result that you're ending up with is an expression for the thermal conductivity, which is basically, formally it is the same as the equation that we are most familiar with. So you still have a specific heat times a velocity, which is associated to this eigenvalue index alpha, and the mean free path, which is going to tell you the distance at which heat flux is propagated. So of course, this expression is important because this is telling you precisely the velocity, time, and length scale of the heat flux transport and how it takes place inside the material. And of course, this is basically the same expression of the kinetic gas theory. So you can, in this sense, think at the crystal and the thermal transfer taking place inside of it as a kinetic gas theory, but the gas is not made out of phonons anymore. Now the gas is made out of relaxons. Okay. Of course, by doing this, we also basically introduce a different time and length and velocity scale of thermal transport, and you can start having a look at some application and how this changes how we estimate these properties inside the crystal. So in this picture, they only have a specific heat. So you only have, actually in the same spirit of the kinetic gas theory, you don't require that each particle in the gas has an energy, but only what really matters is how much a single entity is going to change the total energy to move in a region of space which will differ by a delta T of temperature. So it's a more statistical concept. As for whether they have an energy or not, it's something that I'm actually still working about. It's related with the stuff of second sound, which I don't think I will have the time to arrive at the end, but we can discuss that afterwards. It's something that I'm studying. In this case, yes. So at this level, they have... I don't have... well, it just comes out of the equation. So you do the algebra, and turns out that since the eigenvector is coupling all the phonon modes, then you have to integrate basically all the phonon modes to get something that depends only on the index alpha, and in this part, in particular, that index disappears. Yeah. We see next slide. The next slide, we see. Yeah. You mean what is this? Yeah. Well, actually, if you do that, indeed, you get this specific heat. Using the form of the scalar product and the metric in the space that it's a detail I'm not entering into, you actually do exactly that, and the average of the phonon energy along these eigenvectors alpha turns out to be the specific heat and constant. Yeah. Yeah, but yeah, but again, it's a thermal energy. Also, one thing that you might have noticed, maybe not, I'm not talking about quasi-particles, which is another method. So don't, at this level here at least, you cannot see an h bar omega, say, associated to each alpha. So for this reason, I'm talking just in terms of a thermal property. You have, at this level, just a specific heat. Here, yeah, indeed, actually, here I'm just looking at the bulk steady state, which is a very specific region. What I may be trying to say more specifically is that there's no H bar at this level. You don't see H bar, so it's not so easy to introduce energies at this level. But you introduce thermal energies, that's for sure, so that's specific heat. And as for the time scales, so here I'm showing what happens in graphene. So graphene, we have seen it's something like a very pathological case. So this is the spectrum of lifetimes, of phonon lifetimes in blue, and relaxation times in red. So graphene at room temperature. So on the horizontal axis, I'm plotting the values of the time scale, and in vertical axis, their contribution to the thermal conductivity. Of course, to the exact thermal conductivity here, and here the level of the relaxation time approximation, when I can define these lifetimes. And what you can see that, indeed, for the phonon lifetimes, you get something, this is a log scale, so this is actually a very sharp peak, around 10 to 100 picoseconds. And that's the time scale of the scattering dynamics, but we have seen before that this is the time scattering dynamics due to normal processes, which does not necessarily relate with the time scale of the heat flux dissipation, which is an information which instead you can get out of these relaxons. And you can see that it's very different in terms of magnitude. So here you see that the largest contribution happens at several orders of magnitude larger than the time scale you would guess if looking just at the relaxation time approximation. Also, another distinction is that the phonons have contributed with a continuum spectrum to the total thermal conductivity. So here you see a bunch of continuum states contributing to K. Here you see actually, especially in the largest contribution area, you have a discrete spectrum. So there's no continuous way of changing this alpha index. So this eigenvalue index does not need to be continuous, it can be discrete. It is in a part of the spectrum, maybe here it's more continuous. And also you have like extensive contribution from a single relaxon state. So this, for example, contributes alone with 9% of the total thermal conductivity. So actually, you can get away and get 90% of the conductivity just by looking at a set of 10, 20 relaxon states, which of course contains an infinite number of phonons in principle inside of them. But then the collective excitation that you need to look at are just a limited number of them. Now, graphene was special, so what about silicon? So silicon is something which is much more honest and everything works there. Yeah. And if you decrease the temperature, you can expect the thermal conductivity to go up. So you will expect that that these lifetimes are going to be shifted rightwards. And of course, well, this is in a percentage, so maybe it doesn't go up in this graph, but yeah.
This number 20, does that go down as you lower the temperature?
In that sense. I didn't try that because it's quite tricky to converge at low temperature, but if I have to guess,
The other way.
If I have to guess, if you lower the temperature, you might just have a couple of collective states, or maybe one or two very specific, which are going to give you everything. Maybe it will be something which will look like a drifting distribution, plus some epsilon on top of that. That's what I would guess right now. And in a system like silicon, where the relaxation,
You are showing relaxation time of phonons, right?
Yes.
Is it the total relaxation time of both N scattering and Umklapp scattering?
Yes, everything combined.
Okay, I see. Thank you.
Yeah.
So it's different from lifetime, according to your definition, right?
Well, in these relaxation times, it ends up, they coincide, the phonon lifetime and the phonon relaxation time. Then I just told you that the relaxation time is definable up to certain limitations.
Okay.
And then yes, if you want something more precise, you got to go to the other thing. Of course, they are slightly different. This comparison is not completely equivalent because I'm looking at two different quantities. So keep in mind that when you look at this plot. And then yes, everything So this is also something that you can get with the Mathiesen rule that has contribution 1 over tau from normal plus 1 over tau from Umklapp and the isotopic stuff. Also, this is something that will have contribution from the diagonalization of normal, Umklapp, and isotopic scattering. But also here, since we are diagonalizing the scattering matrix, we are mixing much more the contribution from these different processes. And that's also one way to say that if you solve the Boltzmann equation exactly, the Mathiesen rule does not hold. I'd like to explain a bit in more details. Yes?
I have a little bit strange question. So is the relaxation time is always positive?
If it is over,
So is the relaxation time
always positive.
Always positive?
Yeah.
Okay.
It's strictly, it's semi-positive, definitely. So it can be always positive or at most 0. It can never be negative. And
It
also
can be-
this, although I will not be discussing, it's strictly related with Boltzmann H theorem. So these eigenvalues are also a way to decompose the entropy production of the system. So you want eigenvalues to be positive to ensure that the entropy is always produced in the system and can never decrease, basically. That's the physical reason why these eigenvalues are positive.
Yeah, but if we solve the Boltzmann transport equation directly with relative solution, so relaxation, that is full solution of Boltzmann transport equation doesn't give us relaxation time. So if we convert it relaxation time, it can be sometimes negative. Right?
Which relaxation time from
Directly solving the Boltzmann transport equation
iteratively, you
and
mean?
converting it to single mode representation, and relaxation time sometimes can be negative. So if the framework or essential physics in the full solution and the relaxant is basically same, I thought the relaxation time of relaxant can be sometimes negative.
Well, it's a little bit related with this, I would say, right? So if you actually look at the, if you think in the basis of phonons, you are absolutely sure that the macroscopic quantities, which comes after an integral over all possible microscopic states, is going to satisfy the reasonable physical properties. It's true, you could decompose this and maybe try to assign a relaxation time to the phonon, although that will depend very much on the boundary condition you will impose on the system, which will change case by case. So you may not have a way to uniquely construct this effective relaxation time for phonons as you would propose. And then in the end, yes, here you can see you have both a projection of this relaxation time on eigenrelaxons that can have both positive and negative values, but also, yes, these parts which are boundary conditions and that you decide. So you could decide to build them in such a way that this phonon state in one case will have a positive relaxation time, in another case will be negative, and then you can tune in between all the values you want, while these eigenvalues are still uniquely defined as eigenvalues of the matrix. It's tricky.
Meaning of negative relaxation time. I don't get it.
The meaning of relaxation time is
No, negative relaxation time.
the exact relaxation time is how long you have to wait until you will see the heat flux going down to equilibrium. The negative is something that is ill-defined. So if you want to have the definition that I just gave you, so something that decays by 1 over E after you wait a time tau, you need to use this representation in this basis so that you are guaranteed that you will not have weird things like negative effective relaxation times. If you think at how, say, an eigenvector population will decay down exponentially to equilibrium. If you look at what a phonon, a single phonon will do, and how it decays to equilibrium, you can even see something which will go like this, or something that goes like this if you are lucky, or maybe will increase and then decrease. You don't know that. And that will depend on how you will decide to define this quantity. Because it's not well defined in the end, yes, that's the point. I will, okay, I talked for half the number of slides I had, but okay, so let me just maybe go, okay, I will stop definitely earlier, so let me just show, okay, that in silicon you still say these relaxation times, okay, they are slightly different, but they don't change very much, you could say. So there's not much new you could say about silicon in terms of relaxation time, in terms of time scale. But still you have differences if you start looking at velocities. So if you think in terms of the relaxation time approximation, what you learn is that the right velocity scale at which the heat flux is propagating is that set by the speed of sound. So this is 21 in graphene, this is 9 or 8 in silicon, kilometer per second. And the relaxation time approximation will give you something which goes around that velocity scale. The relaxon would scale down everything by a couple of orders of magnitude. So quite different behaviors, both in graphene, where you might expect this, but also in silicon, this is less, I mean, I was also surprised when I seen these results. And therefore, you will also have some difference carried over when you will study the mean free pulse. So how much time do I have? 5 minutes. Okay, so, okay, I'll change maybe the things because I definitely cannot talk about surface scattering, but it's an article that has been published recently. If you are interested, we can even talk about that later, but maybe I will just give, I mean, this is temperature profiles of thermal conductivity that you have seen also in other talks before. Maybe just let me give you just a punchline to make you interested. And basically what I've done is trying to, this is what the typical way we are describing surface scattering. As of the last decades, we have been using the complete expression of the scattering matrix as far as 3 phonons and phonon isotope scattering is concerned, and then you add a kind of a relaxation time of this form to take into account the existence of some finite characteristic size of your material. And this is the result of this dotted line. And I've been, basically, you can see that there is something fishy going on because we are using something which is complete when we describe 3 phonon scattering. And when we decide to describe surface scattering, we just use something which is a relaxation-like approximation. And if you're interested, I made some work about that. And basically, I shifted these values obtained in the dotted lines by this theory by an order of magnitude smaller values, meaning that this might have some consequences up to about an order of magnitude, maybe, in the way we predict the size at which nanostructuring will have an impact on thermal conductivity. And then, since it was also briefly touched by some question about how to associate, if possible, energies, or at least frequencies, first of all, to each of these modes. Well, what I've been trying to do also was to study basically a Fourier decomposition of the phonon population function. If you use this guess for solutions, you can rewrite the Boltzmann equation in Fourier space, and what you find out is that the whole Boltzmann transport equation turns out to be in the Fourier space nothing else but an eigenvalue problem. So you have a set of eigenvectors, a matrix, which is all this stuff acting on this eigenvectors I and a set of eigenvalues omega, which are the frequencies that you have to find out by the diagonalization of this non-Hermitian matrix, meaning that you will get an oscillation frequency associated to this kind of solution, which will give you an oscillation frequency and a decay time. And I also want to point out that in the limit of the wave vector going to 0, all of this just reduces, if you just neglect this part, it's reduced to the relaxon problem that I've been talking about before, meaning that you can associate to each mode a frequency of oscillation and a decay time. And actually, since we are looking at basically some damped wave solutions of the phonon population number, this can actually correspond directly. Basically, this delta n will induce variations in form of a damped wave to the total energy, which will in turn induce oscillations on the temperature. And this means that I actually recasted the whole Boltzmann equation as a set of n oscillations for a damped wave of temperature. So you can view the Boltzmann transport equation as a basis set of n second sound modes and get a dispersion relation, a second sound velocity, decay time, and compare that also with phonon frequencies, and also get a connection on how you could associate in the future a frequency to the relaxons that I was talking about before. Okay, so I think I have run definitely out of time. So the take-home message is basically that you have a lot of normal processes in two-dimensional materials, and then you have a bunch of consequences that derive one after the another. So your relaxation time approximation that fails, sometimes miserably. You have the appearance of these hydrodynamic modes. You have this carrying over of low temperature transport regimes. Low temperature in three-dimensional system are carried over to room temperature conditions if you go to materials of low dimensionality, and this will be hearing for sure more about this. And since you have this disconnection of how the heat flux is dissipated and the phonon scattering dynamics, then we are also proposing to stop looking at phonons as the heat carriers and then introduce these eigenvectors of the scattering matrix, so relaxons, which can describe the thermal conductivity in terms of the kinetic gas theory out of this gas of relaxons. And this you can ask me about later about the last point. Okay, so thanks for your attention and thanks for very constructive questions.
Thanks very much for the informative talk. Any questions?
I have two questions if time allows. My first question is, when you consider the scattering, the surface effect, you show that your model can predict higher thermal conductivity than just simple homogeneous boundary scattering, right? So can we go back to the slide? I don't remember the slide
I
number.
don't know if the discussion could be clear for everybody, since I didn't enter the details. But if you are asking something about this?
Oh yeah, that one. So yeah, previously people just assumed the homogeneous boundary scattering, as you mentioned, right? And that boundary scattering rate is just simply V over L, which is the lower limit of boundary scattering rate. Because depending on the position of phonons, the distance between phonon location and boundary can be much smaller than L, right? So I thought this model can predict lower limit of scattering rate, but actual thermal conductivity is lower than the thermal conductivity is lower than your calculations. So can you explain why actual thermal conductivity is higher than just homogeneous simple boundary scattering case?
I cannot explain that in 2 minutes. But I can discuss with you later, maybe,
Sure, yeah.
because there were like 15 slides to arrive to this point.
Okay.
So I just wanted to show you that, you know, there might be something also here, but I'm just leaving the last punchline, but without explaining
Okay,
that
sure.
too much.
Yeah, thanks. I think I have to give the others.
You lost your chance.
I guess your conclusion slide, you mentioned phonons are not really good and relaxons are better because they consider as eigenvectors of a scattering matrix, it's good to consider heat. But on the other hand, phonons can relate to the symmetry of the crystals and the whole Brillouin zone. When you find this relaxon and you find there are 20 of them that are dominating, if you go back and look at where, which phonons they are made of, which dominant phonons, does it tell you something?
Well, again, so one could look at it in 2 ways. So if you want to construct an alternative explanation, you could even, to some extent, try to forget some details about the phonons. If that's what you want. Of course, you can also, anyway, ask your question, what are the phonons that contribute the most? And in fact, this plot here, and this was actually the relaxon of graphene, which was contributing like with a relaxation time of about 1 microsecond. So it was with like 7% of, I don't remember exactly, to the thermal conductivity. So here you can reconstruct that in this system here, all these phonons were contributing collectively to a mole with 7%. Of course, if you just want to look at the what does happen around the flexural phonon modes in the long wavelength region, then you might also have to average out over all the relaxon states if you want to reconstruct how much they contribute to the phonon. Of course, you can do that, because in the end, they are all related by a rotation, so you can work your way back to understand and explain things if you are interested in terms of single phonon properties. And here we have a different way of decomposing microscopically the thermal conductivity in such a way that you have all these properties which are associated not to the single phonon but to the bunch of phonons which constitute one eigenvector. And of course you can rotate the basis, so you can decide to reconstruct the 2 pictures with some properties which are going to hold in one picture and others being well definable in the other, so depending probably on the case you look at.
Excuse me, your last slide you have written that the relaxation time approximation cannot be used for 2D dimensional systems. I mean your last slide.
In the
conclusion. By I didn't get. You mean single mode relaxation time approximation? I mean, we have seen many plots for thermal conductivity of graphene, which is obtained by using the scattering, the relaxation time approximation, and it is in good consistency with experiment. I can get how you justify them. I mean that you say that the relaxation time approximation does not hold for 2-dimensional systems, but we have seen many plots for thermal conductivity of 2-dimensional systems, and they are in good consistency with experiments.
So again, it's again for silicon, for example, if you are interested in looking at the thermal conductivity only, that works
not
fine.
Only, I mean the
if
mean
you
free
already look at,
or-
yeah. Let me show this plot maybe again. Here we were even looking at graphite, for example.
Yes,
Uh,
but
the- well,
Is that the fact that relaxation time approximation does not hold, does it hold for any 2D material or is it just for graphite?
why, what is the reason why there should be more normal processes, maybe?
you know, I've seen in for graphene a plot which is good consistency in experiment. It is obtained from phonon Monte Carlo using the scattering time.
Well, maybe you
Relaxation.
can, we can show me this article and so I can have a look at the specific example that you have in mind. But I would say that especially in this case, for example, if you look at graphite, I'm using first principle parameters, so I don't have the freedom to adjust the results I have in that case, and the only way to go on top of the experimental data was to play with the theory rather than playing with the parameters, because if DFT gives me something, yeah, I could scale that. That could be one way of fixing problems, but I can also have something to say maybe about the theory, which also gives insight anyway. And then, of course, maybe if you look at some trends might be well reproduced, some other trends may not. Maybe, yeah, if it works, you publish it, and if it doesn't, you don't. So that could also be a way of looking at that. If something similar could hold for charge transport, yes, and in fact, if you look at some works that have been published last year by, I can give you some references. There have been studies of hydrodynamic motions of electronic transport at low temperature that has also been observed experimentally, because there it's also much simpler to just put an electrical probe and see with much greater detail how the electrical flux is developing inside the system, and so they could see vortices and backflows and other hydrodynamic features that are quite related with the stuff I've been talking about. Yeah. Thank you.
And we'll see you at 2. No? 1:30. I need